Hello everyone, welcome back to Must Electronics. Around 250 GB of source code, 800 plus repositories, thousands of directories. When most people see this for the first time, they have no idea where to start. Which directory does what is the relationship between them, where does Android actually begin? In this episode, we are going to walk through the entire AOSP source tree, every major directory, and I will show you not just what each one contains, but open real files inside so you understand exactly what lives where. By the end of this episode, you will be able to look at any file path in AOSP and know exactly what layer of Android it belongs to, what its job is, and how it connects to everything else. Let's get into it. First time I saw this, I had no idea where to go. You just downloaded around 250 GB, you open the folder, and you see this. Here is the thing, you do not need to understand all of it. You need to understand the pattern. Once you see it, the whole tree makes sense. Every directory here falls into one of three groups. Group 1, the Android layer you already know from episode 2. Frameworks, system, packages, hardware, kernel, device, vendor. These map directly to the architecture diagram. Each one is a layer. Group 2. What makes Android compile? Build, pre-builds, toolchain. These are not Android itself. They are the tools that build Android. Group 3. What Android runs on top of? Art, bionic, external. Art is the runtime that executes your app. Bionic is Android's C library. External is every open source dependency Android uses under the hood. Three groups, that is the entire source tree. Now let's open each one and see what is actually inside. We start with frameworks, the most important directory for anyone who wants to understand how Android works above the kernel level. The most critical subdirectory here is base. This is the core Android framework, the thing most people mean when they say the Android framework. Core contains fundamental Android classes, context, intent, bundle, activity, service, broadcast receiver. Every Android app uses these. Look at this: app, content, OS, Weave. These are the Java packages you use when writing any Android app. This is their actual source code. Let me show you how big one of these files really is. Let's look at activity.java. The class every Android developer has extended at some point. Over 8,000 lines, that is the complete activity implementation. Every lifecycle callback, every window interaction, every intent handling, all in that one file. Now let's look at services. This is where Android system services are implemented. Each of these directories is a major Android system service. AM, Activity Manager Service, manages app lifecycle, tasks, and processes. PM, Package Manager Service, manages app installation, permissions, and queries. WM, Window Manager Service, manages every window on the screen. Power, Power Manager Service, controls wake logs, screen timeout, and sleep. These are all started by one class. Let me quickly show you how large it is. System the process that starts every one of those services when Android boots. We will dedicate a full episode to this later in this series. For debugging in Android, we will be using ADB Logcat. We will discuss about it later in the series. Now a quick question. When you run ADB Logcat and see thousands of log lines scrolling, where does each one of those actually come from? Your Java code calls log.d. That call goes somewhere. Let me show you exactly where. This is system, the native C and C++ layer underneath the framework. The most important subdirectory is core. The one that matters most is init directory. This is the Android init process. The very first user space process the kernel starts after boot. Before Zygote, before system server, before anything else, init runs. It reads init.rc files and launches every other process on the device. Main.cpp is where init begins execution. Service.cpp handles starting, stopping, and restarting every system service. Action.cpp handles the trigger based rule system in init.rc files. Things like on boot start service flinger or on property set do this. Now back to that question. Where does log.d actually go? Here, liblog. When your Android app calls log.d or log.e, that Java call gets translated into a JNI call into this C++ library. Liblog writes the log entry into a circular buffer maintained by the kernel. ADB logcat reads from that buffer and streams it to your terminal. That entire chain log.d to your terminal starts right here in this directory. Here is something that surprises most people. The settings app on your Android phone, the dialer, the camera, the launcher, they are all just regular Android apps. Same structure as any app you would build yourself. Let me prove it. Every folder here is pre-installed Android system application. Now let's open settings and see what is inside. Android manifest.xml, src, res. This is exactly the structure of any Android app you have ever written or opened. The settings app is just an Android app. The launcher is just an Android app. The camera is just an Android app. The only difference is that these are baked into the system image. So they start with elevated system level permissions that no app installed from the Play Store can ever get. That is why settings can change Wi Fi state, modify system alerts, and access device admin APIs because it is compiled alongside the OS, not installed on top of it. This matters because later in this series, when we modify Android, this is exactly where we come to make changes to the built in apps. Here is a question worth thinking about. Android runs on phones from Samsung, Qualcomm, MediaTek, and now Raspberry Pi. Each of them has completely different camera hardware, different audio chips, different sensors. How does the same Android framework code work on all of them? The answer is in hardware. Every hardware subsystem Android supports has a formal interface defined here using AIDL. Think of it as a contract. The Android framework says, I don't care what camera chip you have. As long as you implement this interface, I'll work with your hardware. The device manufacturer writes the implementation for their specific chip. The framework calls the interface, the driver handles the hardware. Neither side needs to know anything about the other. Let's open the camera interface. A manufacturer building an Android camera puts their code here. A Raspberry Pi camera driver implements this interface. A Samsung camera driver implements this interface. A Google Pixel camera driver implements this interface. They are all completely different code, but the framework above them only ever sees this one interface. This is the single biggest architectural decision that allows Android to run on thousands of completely different devices. Here is something most Android tutorials never tell you. When your app starts start activity, it does not go directly to Activity Manager service. It goes through a kernel driver called binder. Every single IPC call in Android, every service call, every cross process communication goes through binder. Without it, Android cannot function. Binder lives in kernel. Let's look at where. For our Raspberry Pi build, the kernel source itself is managed separately by the Raspberry Vanilla project. The kernel directory here contains JKI config fragments and pre-built kernel binaries. The Raspberry Pi specific kernel setup is here. Regardless of where kernel source lives, three Android specific additions are always present in the kernel. Binder, the IPC driver. Your app talks to every system service through this. Without Binder, you cannot start an activity, you cannot display a window, you cannot play audio. Binder connects everything. ASHMEM. Anonymous shared memory allows processors to share data without copying it, critical for graphics performance and media. Wake logs let apps and services tell the kernel, do not let this device sleep while I'm doing something important. Your alarm clock relies on wake log to fire at 6 a.m. even when the screen is off. These three things do not exist in standard Linux. They are what turn a Linux kernel into an Android kernel. Device directory is where specific board or product is brought to life. Everything we have logged at so far is generic Android. It knows nothing about any specific piece of hardware. Device directory is where you tell the build system, we are building for this board, with this hardware, with these features. Boardconfig.mk. This is the most important file in the device directory. Let me quickly find the architecture lines inside it. ARM64. That is what we are building for, 64-bit ARM. Boardconfig.mk also defines which kernel config to use, the sizes of each partition, and how the boot image is assembled. Change one value in this file, say the system partition size, and your device either boots or fails to mount its file system at runtime. AOSP RPA4.mk defines which apps and features go into the system image for Raspberry Pi 4. RAM disk directory contains the root file system and fstab, the partition mount table that tells Android how to mount system, vendor, and data at boot time. Let's open mkimg.sh. This is the script that assembles the flashable SD card image you saw in episode 3. Boot img, system img, vendor img all combines into one file by this script. Every device has something like this. It is what makes AOSP a real product rather than just a collection of compiled binaries. Here is a fact that explains why you cannot just take AOSP and flash it onto a Samsung Galaxy or a Qualcomm device. On a real phone, vendor directory contains hundreds of proprietary binary blobs, precompiled GPU drivers, modem firmware, camera processing libraries that the manufacturer will never release as source code. Without those blobs, Android boots, but the camera does not work, the GPU runs at a fraction of its speed, and the modem is dead. For our Raspberry Pi build using Raspberry Vanilla, vendor directory is much leaner. Here you will find RRO overlays, runtime resource overlays. These override default Android framework values, things like default screen brightness, audio settings, or feature flags without recompiling the framework itself. You will also find product makefiles that define exactly what goes into the final image. This is lean compared to a commercial device, but the principle is same. Vendor directory is where device specific non-AOSP pieces of Android live. Two more directories that are essential to understanding what makes Android unique. First, Art directory. Art, the Android runtime. Before Android 5.0, Android used a runtime called Dalvik. Dalvik interpreted .ex bytecode at runtime. Art replaced Dalvik. it compiles .dx bytecode into native machine code either at install time, at first boot, or as background task. The result runs directly on the CPU, no interpreter in the way. That is why Android apps now start faster and run smoother than they did in Dalvik era. When you build an Android app and produce an APK, inside that APK is a .dx file. Ad's job is to turn that DX file into something that CPU can execute directly. DX2OAT directory is the compiler that does exactly that. Second, Bionic. Bionic is Android's C library. On a regular Linux system, the C library is glibc. Android does not use glibc, it uses Bionic. Bionic is smaller, faster, and licensed under BSD, which allows device manufacturers to use it in proprietary products without the GPL obligations that glibc carries. Every native binary on Android, whether it's init, a system service, or a native library, is linked against Bionic. It is the lowest level of user space code that runs on Android. Two final ones, and these are actually interesting. Build directory is the build system. When you run make in the next episode, this is what wakes up and orchestrates everything. Soong directory, which is the Android's modern build system written in Go. Build rules are written in android.bp files using a language called Blueprint. Make directory contains the older makefile based rules that Soong hasn't fully replaced yet. When we run make in the next episode, Soong reads every android.bp file across all 800 plus repositories and figures out exactly what needs to be compiled in what order with which flags. Then it hands that off to Ninja, which runs the actual compilation in parallel. Now, external directory. You will recognize almost everything here. SQLite directory, the database engine every Android app's room database sits on top of. Zlib, compression, used for APK decompression, network storage. Boring SSL, Google's fork of OpenSSL. Every HTTPS connection on Android goes through this. libpng and libjpeg. Every image your app displays is decoded by one of these. WebRTC, video calling in apps like Google Meet. These are all projects you know. They are bundled directly into AOSP, so the build is fully self contained, no internet required once you have the source. Let's tie it all together. When an Android app calls start activity, the call enters framework based directory, the application framework. The framework communicates through binder, a kernel driver in kernel directory. Activity manager service in framework based service directory handles the request. The new app process is forked from Zygote, which lives in framework based directory. The app's bytecode is executed by art directory. Any hardware app touches goes through hardware interfaces in hardware interfaces directory. The hardware driver itself lives in kernel directory. And underneath all of it, every system call goes through bionic directory, the C library that sits between user space and the kernel. Every directory we walk through today is part of that single chain. Nothing is isolated. Every layer depends on the one below it. You now know what the AOSP source tree looks like from the inside. Not a diagram, not a slide. The actual directories, the actual files, and why each one exists. Here is what I want you to take away from this episode. All 250 GB of this source tree has one job to produce those 4 image files you saw in episode 3. Boot IMG, system IMG, vendor IMG, and the flashable SD card image. Every directory we walk through today contributes something to those files. Frameworks directory becomes system.img, kernel directory becomes boot.img, hardware and vendor becomes vendor.img, device directory tells the build system how to assemble all of it. In the next episode, we are going to watch the transformation happen live, the Android build system, Zoom, Ninja, and Blueprint files. How do you tell the build system what to compile? How does it know the order? How does it handle 800 plus repositories at once? That is episode 6. If this video was useful, please like the video and subscribe to Must Electronics.